Welcome back. So today is our last set of online classes. I'd like to finish up our short unit on gravity, but before we do that, I'd like to remind you about the various assignments that you have left to do. So you have an extra credit homework assignment, so that's going to be due on Monday, May 10th at 10 a.m. The extra credit homework either replaces your second lowest homework grade, or it counts as a 5% bonus to your homework score, whichever improves your grade the most. The extra credit homework is posted in the homework directory. The classwork assignment that is associated with this class, so that will close at 10 on Tuesday, May 4th. And also the post-assessment is up. So if you did the pre-assessment and you then do both of them, both the pre-assessment and the post-assessment, then you get a 0.5% bonus. And so last, we have the final exam. So the final exam is via the Respondus Lockdown browser, and it'll be just like the midterm. The exam is on Monday, May 10th, and it will run from 9 a.m. to 8 p.m. The exam is timed for 3 hours, and the exam will be cumulative, so material from the first half of the course is fair game and will make up about half of the exam. So we've decided, you can use your scientific calculator, so you can have some blank scratch paper and a scientific calculator, but the smartphones are expressly forbidden. Okay, so be aware of those assignments, and good luck with them. So up until this unit, we have treated gravity as a constant acceleration of 10 meters per second squared. This is a good approximation. Okay, we've simplified the math a bit for this course. The real value is 9.78 to 9.83 meters per second squared, with variations due to the rotation and due to the Earth not being a perfect sphere. The Earth bulges at the equator and has a slightly larger radius, while at the North Pole it has a slightly lower radius. The larger effect is the centripetal force, reducing g at the equator to 9.78 meters per second squared, while it's about 9.83 meters per second squared at the poles, but both effects are measurable. The point is, we have thought of gravity as a field. A field tells us that if we put an object of mass m into the field, it will tell us the size and the direction of the force. That is, any object with a mass m in this gravitational field experiences a force of the mass times the gravitational acceleration, and that force is pointing straight down. So we can think of this field strength as being the gravitational acceleration, and the direction is down. We would like to broaden our view and know what the gravitational field is at any distance r from a mass. So every mass creates a gravitational field around itself, and that has a value at every point in space, whether there's another mass there or not. So this field tells us the strength and the direction of the gravitational force that would be applied on a test mass, which is just a way of saying that what would the force be on an arbitrary mass. So to find the field strength, we take Newton's law of gravity. So force is equal to g times mass 1 times mass 2 divided by r squared. And then we divide both sides by mass 2, so we know what the acceleration would be. That means the acceleration is g times mass 1 divided by r squared. The direction of the acceleration is going to be towards the center of mass of the object, generating the field, because gravity is an attractive force. The direction and strength of a field is often displayed using field lines. The image here shows the gravitational field lines pointing towards the center of the Earth, because that is the direction that the mass would be pulled. You'll notice that as the lines get closer to the Earth, the lines get closer together. That is because the closer the field lines, the larger the field strength. The larger the field strength, the larger the acceleration. Okay, so we have an example to do, and also a sanity check. Using Newton's law of gravity and the mass of the Earth, 5.97 times 10 to the 24th kilograms, and the radius of the Earth, 6370 kilometers, we want to calculate the gravitational acceleration at the Earth's surface. Okay, so the force is the gravitational constant times the mass of the Earth times the mass of whatever we're accelerated, divided by the distance of the Earth's center, squared in meters. To find the acceleration, we want to divide by the mass of our object, so we get the acceleration is g times the mass of the Earth divided by the radius of the Earth squared in meters. So to put in our numbers, we multiply 6.67 times 10 to the minus 11 times the mass of the Earth 5.97 times 10 to the 24th kilograms, divided by 6.67 times 10 to the 6.37 times 10 to the 6th meters squared. So if we do that, we find that we get an acceleration of 9.81 meters per second squared. So that's pretty close to right. So this passes our sanity check. Okay, so you have a version of this question to do on the International Space Station. So you'll be finding the value of g at a different altitude. Notice that when you are orbiting the Earth, gravity is still accelerating you. The thing is, gravity is accelerating both you and the spaceship that you are in at the same rate. So you would be in free fall, and you would, effectively feel like you're floating. The point is, gravity is still accelerating you, just that there's no relative acceleration between you and the floor. On Earth, you are accelerated by gravity, but the ground is fixed in place. So in space, it's kind of like you are diving in an airplane or a roller coaster, where you and the airplane are falling at the same rate. Only in orbit, you can do that for a very long time. There's also a question about the relative g on different planets. Okay, good luck with your questions.